Namaskar and welcome to this lecture on concrete engineering and technology. In this course, we are trying to study fundamentals of concrete, proportioning of concrete mixes, stages in concrete construction, special concretes, mechanisms of deterioration in concrete, reinforcement of concrete structures, maintenance of these structures and so on, in light of the developments that have taken place in the field of science, cement chemistry, admixtures and so on. As far as our discussion on revising the fundamentals of concrete is concerned, we are trying to do an overview of this course, constituents of concrete, cement, sand, coarse aggregate and water, in addition to chemical and mineral admixtures, properties of fresh and hardened concrete, hydration of cement and strength development, and quality control in concrete construction. Out of that, our discussion today would focus on a topic which spans between properties of fresh and hardened concrete and hydration of cement and strength development. One must remember that in a complex material like concrete, it is very difficult to classify and stick to that classification in a watertight manner. There are subjects which span one or more compartments. For example, hydration of cement is the basis on which strength development takes place, on the basis of which special concretes can be designed and so on. Quality control of concrete spans constituents, methods, properties of concrete and so on. So, the discussion today would be on the pores and porosity in concrete. What we will talk about is the origin of pores and porosity in the material, and we will talk about the nature and characterization of these pores, and finally, the measurement of porosity in concrete. So, this is an outline of what we would be talking about in this discussion. Now, beginning our discussion with the origin of pores and porosity in concrete, let us look at the volume changes that take place when C3S and C2S, which is the tricalcium silicate and the dicalcium silicate, they hydrate. Now, these equations here give us the chemistry of hydration of these products. As far as C3S is concerned, C3S plus 5.3 H2O gives us CSH, which is the calcium silicate hydrate gel, and 1.3 times CH, which is calcium hydroxide. So, if we look at the mass, this equation, these numbers here tell us what is the mass balance involved. From the density considerations of these individual constituents, we get the volume changes that are involved when C3S hydrates. If we look at this total here, we have 73.2 cc of C3S reacting with 95.5 cc of water, which means that the volume of the reactants is 168.7 and the volume of the products, which is given here, is only 162.7, which means that there is a net change of about 6 cc as far as the hydration of C3S is concerned, and that is a change of about 3.6%. The volume after the reaction becomes slightly smaller than the volume before the reaction. Similarly, in the case of C2S, we have 130 cc of reactants reacting and finally giving us 129.6 cc of the products. Here the volume change is much smaller, it is about 0.4 cc and it is about 0.4% or whatever, and here too the volume after the reaction becomes smaller than that of the reactants. Now, what are the implications of this change in volume as far as concrete is concerned? In addition to the volume changes that take place on account of the hydration of the different phases of cement or different solid complexes of cement. See, C3S and C2S, which we saw just now, are two of the important solid complexes making up the cement. The other two being C3A and C4AF, the tricalcium aluminate and the tetracalcium aluminopherrites. In addition to these volume changes, one must remember that the water added to concrete is far in excess of that required for the hydration of cement. Hydration of cement from a chemical point of view or the point of view of chemistry, stoichiometry. If we read different reference papers, books, we would find that the amount of water which has been cited to be required for the complete hydration of cement varies from say 18% to 22% by weight of cement, which basically means that in order to hydrate 100 grams of cement, different people have different values to quote, but the value of the amount of water required for the hydration of that cement varies from about 18 to 22 grams. In contrast to that, in concrete, the water added ranges from 40 to 55% in most cases. That indeed is the water cement ratio. When we talk of water cement ratio in concrete, what we are talking about is how much water and how much cement is present in the concrete by weight. Now therefore, even if we assume complete hydration of the cement, a lot of water remains in concrete after the hydration is over. This picture here, or this set of pictures here, shows us the volumetrics of cement hydration. It is a schematic representation and should not be taken too literally. If we have a certain amount of cement, we add a certain amount of water to it. This is the picture before hydration. Once the hydration starts, the cement comprising of C3S, C2S and whatever it is, that starts getting converted to hydration products. And since in this picture we are talking of an intermediate stage where all the hydration has not yet taken place, there is some unhydrated cement, some amount of hydration products which have been formed and some amount of water which is still left. So, some amount of water has been consumed and some amount of cement has reacted with the water and the hydration has taken place. Now, given the fact that hydration, that is the reaction of C3S, C2S and so on, involves a reduction in the volume, we get this amount of volume here, which is basically pore space. So, the amount of unhydrated cement plus hydration products plus remaining water, which is up to this point here, is slightly smaller than the original volume which stood at this level. So, this is the pores which have got generated as a result of changes in volume of the hydration products, or the hydration products occupying just that shade smaller volume compared to the reactants. If this hydration continues, or rather as this hydration continues, we finally have a situation where the hydration ends and we do not have any unhydrated cement. At that point in time, the hydration products have all formed. This amount of pore space which is arising out of the changes in the volume of the reactants and the products has slightly increased from this level here to this level as shown, and this amount of water is the unreacted water which is still remaining in the cement paste. Cement paste is the material that we are talking about in this picture. We are talking only about water and cement, what happens to them as the hydration goes on from the initial point to an intermediate point to a point where complete hydration has taken place. In that case as well, there is a certain amount of water which is still remaining, and this is the amount of water which was added in excess of that required for complete hydration. Now, why was that water added in the first place? That water was added to provide workability to the concrete. Those of you who have carried out experiments, and I will encourage you to do that, if you mix ordinary Portland cement with say about 30% water or 27% water, you will find that the dough or the paste that you get is highly unworkable. We cannot really use it the way we would like to use concrete, and concrete is just nothing but sand and coarse aggregate added to that paste. Only when more water is added, the paste becomes a little more flowing, and at 40%, 45% it becomes such that even if we add sand and coarse aggregate to it, the concrete still remains workable. So, having said all that, let us take a look at what happens in cement hydration very quickly. This is a cement particle surrounded by water, and as far as concrete is concerned, we can consider millions of cement particles really suspended as far as concrete is concerned in water. If the cement particle is now considered spherical and is surrounded by water, hydration begins at the surface of the cement and leads to formation of hydration products which are deposited on the cement particle. This portion here is the portion where you may say reaction has taken place or the hydration has taken place, and the cement particle has now shrunk to the size which is shown here, and this is the volume of hydration products, which is just a shade smaller than the cement particle and the water volume together. For more hydration, that is, once these hydration products have been deposited on the cement particle, water from outside needs to move through the previously formed hydration products to find new surface for the reaction. So, basically water moves from outside and finds new surface here, and then at another point in time we may have a situation where more cement has been hydrated. Of course, the model can also include the idea that some reactions continue to occur within the reacted zone. So, as the water moves through this layer of hydration products, it is possible that some of the water is also used up in supplementary reactions or secondary reactions within the reaction products or the hydration products, and only part of it reaches the fresh surface of cement and continues the hydration there. So, this discussion, which is a schematic representation or a very highly simplified understanding or an explanation for the hydration of cement, is relevant because at some point the reaction will stop, that is, hydration stops. Now, this could be on account of exhaustion of water, that is, the water that was available here is finished. We do not have any water left in the paste or the concrete, or the exhaustion of cement, that is, the reacted layer over a period of time will become larger, the unhydrated cement particle would continue to shrink, and there would be a time when there is no more cement available for hydration. At that time also hydration basically stops. There is a third possibility, and that is the reaction products which are formed here, they acquire properties that make it difficult for water to move through them to the fresh cement surface. That is, even though there is unhydrated cement here, there is water available here, but this water cannot move through the hydration products. the hydration products have acquired such properties, that is, they have become so dense, and even then hydration would basically stop. Now, what this model brings out is the fact that movement of water through the hydration products is essentially through the pore spaces within them. How else would water move through hydration products? We have to have spaces between them, and these spaces are precisely what are the pore spaces within hydration products. The hydration products are not solid in that sense. Even at the end of the hydration process or the hydration reaction, there is always a possibility of unhydrated cement being left over. So, especially in a situation like this, it is likely that there will be an unhydrated core of cement left behind, which means that the cement is still there, water is still there, but still there is no more hydration taking place. And that, in the diagram that we used previously, is the situation that is shown here, that the hydration has ended, but that does not mean that the cement has exhausted. There is some unhydrated cement still left here, but even in that case, some amount of excess water will be there, some amount of pores which have been formed on account of shrinkage of the products or the hydration products with respect to the volume of those reactants will still be there. So, nothing really changes as far as our understanding of the genesis or the origin of pores in cement paste is concerned. It still remains true that the water that is added is in excess of that required for the hydration, and at the end of the hydration process, on any account, complete hydration of cement, or even if there is unreacted cement left behind, some amount of water remains behind in concrete or the paste which is unreacted. That water having been added to provide the required workability to the material. And this is what is the picture, that even at the end of the hydration product, even at the end of the hydration reactions, whether it is complete hydration here of the cement or it is unhydrated cement left behind, this part is still true. We still have this space which is available to us or which becomes available. Now, as far as this excess water is concerned, which is available in the matrix, what happens to that? It is the removal of this water from the concrete over a period of time through evaporation and so on, that is at the root of the pores that are formed in concrete. So, this water which is left behind gradually evaporates, and this evaporation of water leads us with the concrete or leaves us with a concrete which has pore spaces which were otherwise occupied by the excess water. This discussion that we have had about more water being added to provide workability, some of it remaining behind at the end of the hydration process, clearly establishes that the pore space in concrete will be higher in cases the water cement ratio is higher. If we add more water, that is, we increase the water cement ratio, the amount of water that is left behind at the end of the hydration process will also be more, and that qualitatively establishes a basis for the water cement ratio versus strength relationship. What is the water cement ratio versus strength relationship? It says that if we increase the water cement ratio, the strength reduces. I mean, whether it is linear or not is a different matter, but the strength goes down, and this strength is related to the pores. And now we have seen that if the water cement ratio is higher here compared to this point, the excess water available over and above that required for the hydration of cement is higher, and therefore, the pores will be more, and therefore, the strength will be less, because intrinsically, because strength is related to porosity through an expression which is something like this. which says strength S is equal to S naught times the exponential of minus k times P, where P is the porosity, K is a constant, and S naught is the intrinsic strength of the material. Now, this is something which we will deal with more when we talk about the strength of concrete, not so much when we are talking really about the porosity today or the pores and their genesis, but yes, through this discussion we have established a qualitative reason for the decrease in strength as the water cement ratio is increased. Let us take an illustrative example. If we add 180 kgs of water per cubic meter, and that is a normal water content as far as concrete is concerned. If we use 400 kgs of cement with that, and if we assume that 20% by weight of cement is the amount of water that is required for complete hydration, this value becomes 80 kgs, because we are using 400 kgs of cement, 20% of that is 80 kgs. So, 80 kilograms of water will be consumed and 100 kilograms, 100 liters of water will be left behind. In another situation, if for the same cement content we have added 200 kgs of water, which means that the water cement ratio has increased, there is more water, this mix is more workable, the amount of water that is required for the hydration is still the same, because we have not changed the cement content. We still need only 80 kgs for hydration. The amount of water which is left behind is 120 instead of 100. So, this will finally have more pore spaces, because in this case 100 liters of water will escape, in this case 120 liters of water is available for escape. Now, what this example tells us is that as much as 100 liters of water is available for escape in a concrete containing 180 kgs of water and 400 kgs of cement per cubic meter, and that is as much as 10% of the volume of concrete. We proportion the concrete for 1000 liters, that is 1 cubic meter, and if in this 1 cubic meter or 1000 liters there is 100 liters of water which is available to escape, that is a huge amount of water which is available to escape. Well, whether all of it escapes, whether all of it can escape and so on is a different story. Even if the water remains in the concrete, it can at best be said that that concrete is one which has pores saturated with water. The concrete still has pore space. So, the fact that water is present in those pore spaces does not take away from the fact that pore spaces have been formed. That space is not solid hydration products. Of course, as I said just now, not all excess water may escape, being trapped between layers of hydration products and so on. The bottom line is the pores in concrete are not negligible. The extent of porosity in concrete is not something which can be ignored. It has to be something, or it is something which needs to be studied, it is something which needs to be better understood, and that is what our focus is today. Now, this is a picture of how people try to model these pores and pore structures. These here are large aggregates, they could be sand particles for all you know, it really does not matter. As far as cement matrix or the cement paste matrix is concerned, the white portion here is all cement paste, and this is what becomes what is shown here in this detail. There are hydration products and there are pore spaces within the cement matrix. Another model by another researcher is shown here, where there are aggregates, there is cement paste, there is free water, there are empty pores, there are saturated pores and so on, and this here is some kind of a representation of the different phases. There is aggregate, there is unhydrated cement, there is hydrated cement, there is chemically bound water, there is gel water, free water, empty pores and so on. So, beginning from this point onwards, this is cement paste. Unhydrated cement does not count in cement paste, and it depends on the definitions that we take. Free water and empty pores have been called pores in this reference. As far as this side is concerned, it says evaporable water and non-evaporable water. So, non-evaporable water is that which is chemically bound. There are hydration products which hold certain amount of water within them, which is chemically bound, and that chemically bound water cannot easily escape, but the other can escape. So, once we understand this kind of a model or this kind of a schematic representation of what we are talking about, we are prepared to embark on a more detailed discussion of pores and porosity. Let me also show you this piece of concrete once again, and what we have been showing through these pictures just now is the blow up or a very highly magnified view of portions such as this, where there is aggregate, there is a matrix, and the pores that we are talking about is the pores in this matrix, because it is in this matrix that we originally had water and cement, and this is where the hydration has taken place. This is where the hydration products have been formed, some of which were slightly smaller in volume compared to the reactants. This is where there is excess water which is trapped. Some of it is trapped within the reaction products and has not escaped, some of it has already escaped, and so on and so forth. So, keep it in mind that this is the small area that we are talking about when we are talking about pores and porosity in concrete. Now, having done this discussion on the origin of pores and porosity in concrete, let us try to understand a little bit about the nature and characterization of pores in this material. This is a picture that we have seen before and is nothing but an idealization or a schematic representation of the piece of concrete that I actually showed you. We have aggregates here, we have cement paste here, and the cement paste is shown here, which shows CSH and all kinds of hydration products sitting here, and there are pores within the HCP which may or may not be filled with water, and of course, there is some water which could be sitting with the hydration products such as here, which has been called chemically bound water. In addition to these pores in the hardened cement paste, there is also a transition zone which is around these coarse aggregates, which has properties which are different from the main HCP, and that has another kind of pore space, and that pore space varies only from the point of view of size. Now, this is another picture of the evolution of pore spaces and hydration of cement. We have unhydrated cement particles suspended in water. Gradually, the water and the cement begins to react, hydration products begin to form, we reach a stage like this, and then finally we reach a stage like this. There is some unhydrated cement which is shown here, or there are pore spaces within the hydration products, and so on and so forth. If we look at the pores in concrete, we look at literature, we find that the pores in concrete can be divided into 5 classes on the basis of size. There is entrapped air, there is entrained air, capillary pores, gel pores, and intracrystallite pores. And these pores or these pore spaces are varying in size. As far as entrapped air is concerned, it could be as much or it could be as large as a millimeter or more. And entrapped air is precisely what is very dangerous, because the pore size is very large. it is air which is not intentionally entrained. When it comes to entrained air, the size is much smaller, and that is the kind of size that helps us at least to some extent in getting more desirable properties. Capillary pores are smaller than that, gel pores are even smaller, and intercrystallite pores are the tiniest of the lot. If we look at the pore size distribution within concrete, again it is the same picture: entrapped air, entrained air, capillary pores, gel pores, and somewhere here would be the intercrystallite pores. We will study it a little bit more in detail a little later, that most of the space in concrete as far as pore space is concerned is occupied by capillary pores, and therefore it is important for us to understand the evolution of these pores as it goes, as it happens. It is important for us to understand the evolution of these pores as it happens through the hydration. This is yet another picture showing the different pores, different terminologies. There are coarse pores, there are macrocapillary pores, mesocapillary pores, microcapillary pores, mesogel pores, and microgel pores. So, what it really shows is that the porosity or the pores in concrete have attracted the attention of a lot of researchers, and they have used different tools to examine these pores, determine their sizes, try to understand their genesis and their properties, and try to give them names. So, it is not really the names that are important as far as this discussion on concrete engineering and technology is concerned. We are more interested that you are introduced to these ideas, which are becoming so much more important in the modern day concrete technology. It is impossible for a modern day concrete engineer to be totally ignorant of some of these ideas. This picture here is nothing but a concrete slice. You can see coarse aggregate gravel here, there is sand particles here, and so on. And what we are studying on this side here is all hydrated cement paste kind of structure. So, this is a very interesting dimension to concrete engineering of the 21st century, the modern concrete engineering. Entrapped air is unintentional air in concrete. Entrained air is intentional air through chemical admixtures. Capillary pores, they exist within the cement paste and aggregate interfacial zone. The gel pores exist with the gel in the hydration products, and intercrystallites, they exist within the gel. Now, this is an illustrative example of the kind of pore space that exists within concrete. I am going to use this example to illustrate several concepts of pores and pore sizes in concrete. If we take a pore structure A, which is shown here, the model pores are cylindrical. That is, there is a diameter associated with them and there is a volume associated with them. So, the diameter of these pores is the largest, the diameter of these pores is smaller, and this is the smallest. The volume for a cylinder we know is related to the diameter and the length, and if there are more than one cylinders, we can multiply this by a number n to get the total volume. Now, in this case, we can try to determine the volume of these pores, which are the largest, the volume of these pores, which are slightly smaller than that, and the volume of these pores, which are the smallest, provided we know the numbers and we know the lengths. If we have pore diameters d1, let us say the total length corresponding to that is L1, the total number corresponding to that is N1, the volume associated with that would be V1, and V1 would be related to this diameter, length, and the numbers. Similarly, we can have an expression for V2 and V3, and this is a schematic of these volumes and the diameters, that there is a V1 which is associated with D1, there is a V2 associated with diameters D2, and a V3 which is associated with D3. The total pore volume in this system is V1 plus V2 plus V3. So, we have a pore system or a pore structure A, which has diameters of pores D1, D2 and D3. The individual volumes of pores of these sizes is V1, V2 and V3, and the total pore volume is V1 plus V2 plus V3. So far, so good. Now, if we consider a similar structure which is slightly different, let us say B, and there the relative volumes of pores having the same diameters, the same lengths, but the volumes are different. And this can happen if we just change the number of those pores. Initially, we had N1, N2 and N3, and if that becomes M1, M2 and M3, then the volumes will change. And for the sake of illustration, I have made it V2, V3 and V1. Now, how that picture is represented here is that now for pores having a diameter D1, the volume involved is V2. For the pores with diameter D2, the volume is V3, and the pores with the diameter of D3 has a volume of V1. In this case also, the total pore volume is V1 plus V2 plus V3. Now, if we compare these two pore structures, A and B, let us recall what was A. A is a situation or a pore system where D1, D2 and D3 have the lengths and the numbers of pores such that the volumes are V1, V2 and V3. In the pore system of B, the numbers have been so adjusted with the same length that the pore volumes for D1, D2 and D3 have now become V1, V2 and V3 as shown here. So, D1 has V2, D2 has V3 and D3 has V1. Now, if we are asked to compare these two pore structures, what are the kind of comments that we can make? The first thing is that the total pore volume in both cases is V1 plus V2 plus V3. So, there is no change in the total pore volume of the two pore structures. So, the pore structures are the same as far as the total pore volume is concerned. However, in A, the large sized pores occupy a large volume. Large sized pores because D3 is the largest pore size, and in A, D3 has a volume V3 which is the largest. So, if we were to calculate a percentage of volume contributed by the larger pores, it will be the largest as far as the larger pore is concerned for A. Whereas, for B, the largest volume is occupied by the medium sized pores. The largest volume here is V3, of course, that is the way we have defined, that is the way we have modeled. That is now contributed by pores which are medium sized. In A, the small sized pores occupy the least volume. That is, the contribution, the relative contribution of the small pores as far as A is concerned is the least. Compared to that, in B, the large sized pores occupy the least volume. So, we can make any such statement. We will have to study these pore sizes, we will have to study the relative contributions, and then we can make a statement as to how one pore structure is different from the other. Now, how do we understand these concepts in the context of concrete, where the pore structure evolves as a result of the hydration of the cement? Not all cement is hydrated at the end of the day. Concrete is prepared with different water cement ratios, which leads to a varying amount of excess water. Cements have varying chemical compositions and therefore, their hydration products need not be the same. Basically, what we use in concrete is two parameters to characterize the pore structure, the total pore volume and the pore size distribution, the differential pore volume. In our discussion today, we have talked about the total pore volume and the pore size distribution. What we have not talked about is the connectivity of these pores. Now, if you look at this slide once again, which shows the different diameter pores, we must understand that we showed them as not connected. The connectivity of these pores is a very important idea that is important for us to keep at the back of our mind, which is central to understand any porous system or any porous material. It is also important to understand the connectivity facilitates movement of material within the pores. So, standalone pores which are not connected to the pore spaces are not particularly harmful as far as movement of deleterious material within the pore structure is concerned. It is only when the pores are part of a continuous system that they become harmful from a durability point of view as far as concrete is concerned. So, these are some things which we will talk about later. As far as porosity is concerned, now porosity is a measure of the void space in a material and is a fraction of the volume of voids, which is Vv over the total volume Vt. If we have a material which has a total volume of Vt, which has a consolidated pore space of Vv, then the porosity of this material will be Vv upon Vt. We must remember that this Vv is a consolidated pore space which we have put here. Actually, what could be happening is that as far as this material is concerned, there is a total volume Vt and there are pores of different sizes which are present in this material, and they are all contributing a little bit towards this volume of the voids, and they have to be continuous in order that they become part of a continuous pore system. Porosity therefore, will be defined in terms of cc per cc or cc per gram. So, in any case, the pore space will be defined in terms of volume. It could be defined in terms of a volume percentage of the pores to the volume of the material, or it could be defined as volume space of pores to the mass of that material. It can be expressed as a ratio which would be between 0 and 1, or a percentage which would be between 0 and 100. So, having completed our discussion on the nature and characterization of pores in concrete, we need to talk a little bit about the measurement of porosity in concrete, and that is something which we will do in the next discussion. We will close the discussion today with some homework, and that could include study of hydration reactions from the point of view of associated volume changes. What we gave examples, we did give two examples of C3S and C2S hydration. I would like you to look at those hydration reactions a little more closely and also try to understand what is happening with C3A and C4AF. We could read about the pore structure of rocks. After all, rocks have their own porosity, except that in the case of rocks, the porosity does not evolve over time the way it evolves with concrete. It does evolve with time because the rocks are formed under different processes and the pore spaces of different rocks is different. So, that is something which would be interesting to compare the porosity and the pore structure of rocks versus that of concrete, which is an artificial rock. We could read about available hydration models from the point of view of evolution of pore structure in cement concrete. There are different hydration models available as far as simulating the hydration of cement is concerned. These models have been developed with different objectives. Sometimes they have been developed in order to understand what is the best size distribution of particles of cement in order to ensure maximum hydration. They have been developed to study the heat liberated and so on, but we could also study it from the point of view of volume changes and evolution of pore structure. And now, assuming that concrete has pores of different sizes, we could study the relationship between the different properties of concrete, that is strength, shrinkage, permeability, durability and so on, to the different sizes of pores present. Maybe we will find that the larger sizes contribute to something, the smaller sizes are more important for some other property and so on. With this, we come to an end of our discussion. Thank you.